So how many of us saw a speed up yesterday? Okay, great. What was the best speed up you got?
60%.
60%? So 1.6?
Like before the threading it was 1.6 seconds and after threading it was 0.7 seconds.
So speed up is TS over TP, right? So what is the best speed up you got? 1.5. And efficiency? When, how many processors? When 3? 3. Cool. So yesterday we looked at scalability, right? We looked at speed up, which is defined as serial time divided by parallel time. We looked at efficiency, which is S over P, which is serial time divided by PTP. Then we saw that if we increase the number of processors while keeping TS constant, what happens to efficiency? So I'm increasing P while keeping TS constant. It decreases, right? And if I keep increasing TS while keeping, so hopefully it will increase, right? Then we also looked at ISO efficiency function W, which is at the rate at which n needs to grow so that the efficiency remains constant, right? And the lower the ISO efficiency function, the more scalable our program, right? So any questions about this part? Was anyone able to draw this graph, and were you able to observe this in yesterday's lab?
It was not perfectly smooth, but the trend is there.
Trend is there. Trend is there. Okay. So basically the takeaway of last lecture is we should try to remove all the communication and idling, right? So the algorithm we looked at yesterday, when we think about how different processes are executing the algorithm, they were all doing add initially of n by p numbers, right? And then after they are done adding n by p numbers, they send a number, right? So this is the communication overhead. Then we again do a add. We send the number again, and this processor again does a add, right? So these processors are just sitting idle, right? So this is our overhead when we go from parallel execution, serial execution to parallel execution, right? And just looking at it analytically helps us write better parallel programs, right? So the idea is to remove all this overhead as much as possible, right? So hopefully all processors are doing useful computation at most of the time, right? Then you should see better speed up, right? So, but it's also about the structure of the problem, right? So for instance, we can think about this add that we were doing as some sort of a tree-based dependency, right? So when this computation is done, when both these computations are done, only then this computation can start, right? Similarly, when these two computations are done, only then this computation may start, and so on, right? But some of our task DAGs may be completely serial, right? So let us say you can only start this computation when the computation above ends, and you can only start the next computation when the computation above that ends, right? So there is no scope for parallelization. So the best possible serial time in this case is n, where n is the depth of this tasks, and the best possible parallel time is also n, right? You cannot run two things in parallel. So the speed up in this case that you get is 1, right? And the efficiency you get is 1 over p, right? So for this algorithm, there is no way to increase the problem size while keeping the efficiency constant. There is just no way, right? So this is a highly unscalable problem, right? So no matter how many processors I throw at it, the running time doesn't decrease. Right? So you have to be careful when you design your algorithm. So how many of you found the lab hard? Like thinking about all this was pretty hard. It was easy. Okay, some of us found it hard. Anyone else? Yeah, so I yesterday saw different implementations and different way of drawing these DAGs, right? Different way of doing the word counts, right? And all of them have different implications on runtime, right? So doing this can be quite tricky, right? And you also have to worry about locking, synchronization, and all these other things, right? Okay, so now we are done with the analytical model of computation. We have defined speed up, efficiency, and these are useful things to have in our back pocket, right? Anytime we are designing a parallel program. But today, let's come back to reality, right? So, so we were shying away from messy hardware, right? But now let's jump into the reality, right? So we were making certain implicit assumptions, right, when we were talking about this. Right. So first of all, we were assuming uniform memory access. Right. Every worker, it doesn't matter who is doing what, right? So we were assuming uniform memory access, so we are free to place any task on any worker. We were assuming no stragglers, so we were assuming every worker is taking the same amount of time, right? So when we were doing n by p additions, we assume that they complete in theta n over p, right? Because every task that is being done, every worker is equally powerful. But this is not quite true, right? If you look at memory, actually locality matters a lot, right, on real hardware. So when CPU is talking to cache, it takes roughly 1 nanosecond. When it is talking to DRAM, it takes something like 100 nanosecond. When it is talking to a different node in the same data center, this can take 60 microsecond, right? And if it is talking to cross data center, then this can be 5 to 200 millisecond, right? So we cannot just ignore locality, right, which we have been ignoring in our analytical model, right? So one might say that we will just do everything locally, right? So whoever has the data should do the job, right? But that's also not that great. So let us say this is some data which is very hot for the computation, and a particular worker owns this data, right? So now this worker will be asked to do all the work, right? So load balancing also matters, right? You cannot just optimize for locality. You also want to make sure everyone is doing something useful. So if I don't have data, it might be useful to get the data so that I can also do something useful. Then we have stragglers, right? So one machine, if we look at different machines, so let us say this is the time it takes for adding n by p numbers, right? And M2 also takes the same amount of time. But for some reason, M3 takes much longer time to add the same numbers, right? And like we discussed, this can happen because maybe M3 has another concurrent process that is running. So adding numbers is not getting enough CPU, right? Or maybe the fan of the CPU broke, so the OS is throttling the frequency of the CPU, right? Or there might be some faulty disks, faulty networks, bugs in kernel, whatnot, to slow down workers, right? And then finally, we also have faults, right? So uh, someone was supposed to compute addition of n by p numbers, but while it was doing, it just crashed, right? So now our computation is just stuck, and we don't know how to complete this computation, right? So this is pretty daunting, right? I mean, writing a serial program itself is pretty hard, right? To make sure that there are no bugs and there are no security attacks like you were seeing in the last class, hopefully. Right? Writing serial program itself is pretty hard. But now you also have to worry about so many new things, right? You also have to worry about parallelization, right? And scalability. You have to worry about fault tolerance. You have to worry about stragglers. You have to worry about locality. You have to worry about load balancing, right? So, I mean, for this poor programmer, this is just too much, right? So, it's just too many things that they have to worry about while also managing the correctness of the program, right? So I hope at this point you appreciate this problem, right? So you are given thousands of computers, you want to use them effectively, anything can crash at any time, anyone can be slower than anyone else, right? And you have to manage your correctness, and you have to beat your business competitors who are also building the same service as you are, right? So everything is happening under a deadline. And this is pretty bad. So we just got a taste of parallelization yesterday, right? We haven't, so we haven't even looked at other things like fault tolerance, stragglers. But hopefully you appreciated that writing serial program for word count was quite easy. I think we were done in 10 minutes. But writing a parallel program that got us good speed up took quite a while, right? Okay, so what is distributed computation about? So the idea is to save the poor programmer, right? Because they have their own things to worry about, right? They have their own business problem to solve, right? So hopefully, wouldn't it be great if they just write program and they don't have to worry about any of it, right? They don't have to worry about stragglers, fault tolerance, load balancing, locality, parallelization. They just write a program like they write their normal C programs or whatever, and hopefully it just does everything that we hope to do, right? So distributed computation is all about abstraction, right? What is the correct programming language? What is a good programming language such that the programmer doesn't have to think about all of this, right? So any questions so far? Okay, any thoughts how to do this?
Might be having a network of nodes.
Hmm?
like in a distributed system, having a network of nodes and disseminating information or any kind of task. But in that case, it is also becoming more vulnerable to distributed loss attack also, because it might be connected to the network server. So it has
No, network is just a setup issue. So let us say things are connected to network, but you also have to worry about fault tolerance, right? So what if, let us say you had 10 threads, one thread just crashed in the middle. So when you write a multi-thread program, you generally don't think about fault tolerance, right? That a thread can suddenly go away, right? Okay, so let's do this step by step. So the first idea is pretty interesting. So the idea is we already have multi-core systems, right? This is my current laptop, let us say, right? And I already have a shared memory, right? So all CPUs can talk to the same DRAM, right? And I already know how to write multi-threaded programs, right? So some threads are running on some CPUs, right? So we are familiar with writing multi-threaded programs which use a shared memory to do computation. So the idea is, why don't we try to take the same program as it is and run it in a distributed setup, right? So what we will try to do is, now these two CPUs happen to be on a different machine. They're not on the same machine, right? So these two CPUs are on one machine. These two CPUs are on another machine. So some threads can run on the first computer, and some other threads can run on the second computer. But what to do with memory, right? So the threads assume that they have a shared heap, right, and shared code and whatnot. So the insight is, anyways, the memory is virtualized, right? We, when the thread talks to the memory, it doesn't talk to physical memory, right? It talks to virtual memory. So anyways, the memory is virtualized. Can we extend the same virtual memory concept to make it shared across distributed systems, right? So this idea is called distributed shared memory. Right? So the idea is, from the point of view of the thread, they are still in the same virtual address space, right? This thread and this thread, from their point of view, even though they are running on different CPUs, different machines altogether, right? But they are still in the same virtual address space, right? That is the illusion that distributed shared memory will try to create, right? So if we are able to create it, isn't it amazing? This is like, we wrote a multi-thread program for a single computer, and now I can run it on multiple computers without changing the program, right? I just did some magic under it in the OS layer on the hardware, and the program doesn't need to change, right? So let us see an implementation of this. So there are multiple implementations of this. Let us see a page-based DSM, right? So the idea is, let us say this CPU tries to load a particular virtual address, right? So when it tries to load the virtual address, it will first go to TLB, right, to translate this virtual address. But let us just say TLB, we had a TLB miss, right? So TLB doesn't have this virtual address to physical address mapping, right? Whatever we were looking for. And then let us say we have a hardware managed page table. So when when the hardware notices there was a TLB miss, it will try to go and walk the page table, right? So the hardware will go and walk the page table, right? And in the page table, we again have virtual address to physical address mapping. And we also, page table also has some bits, right? Whether a particular virtual address is valid, whether it is present, and so on. So let us say this virtual address is not present, right, in the page table. So typically what the OS page handler does like when the hardware finds that it is not present, it will invoke the OS page handler, page fault handler, and the OS page fault handler typically brings the page from the disk, right? That is the idea of demand paging, right? So we have all this machinery already set up. So can we use this machinery? So the idea of page-based DSM is, instead of getting it from the disk, I will get it. So let me clear this a little. Right, so these are physical memories. So this virtual address was not found in the page table. So instead of getting it from the disk, the OS goes and gets it from the remote memory, right? So from the point of view of the program, nothing has changed, right? I was just trying to load a virtual address. There was a page fault. OS got that page from remote memory, and OS resumes the program, and the program just continues, right? So we just built our first distributed computation system by just taking your regular C multi-threaded program and making it distributed, right? Isn't this exciting? This is quite exciting, right? So our poor programmer didn't have to think about at least some of the aspects of distributed computing, right? They just wrote a program on a single laptop. They tested it, made sure that it works, and added DSM under it, and it just works. How beautiful. Amazing. Right, so basically it gives you familiar programming model. You don't have to do anything. Is whether it is C, Java, Python, it just works, right? And it also gives you identical virtual address space, right? So you can even move this thread from here to here, right? By just moving CPU registers, and we are okay, right? Because we are providing a logical, a unique logic, shared logical address space, right? So the same virtual address that this thread could load on this machine, it can also load on this machine, right? So threads can migrate easily. Okay, so are we done? Looks like we are done.
Can you comment on the performance that will change if we use this setup?
Right. So this DSM was a hot topic in 1980s because of its promise, right? This is an excellent promise, right? If I can say that you just code on a single machine, do whatever, and I'll make it distributed. This is an excellent promise, but of course, it didn't work, and that's why we'll spend some more time on this. So there are several problems, right? So one of the problem is, of course, performance, and a part of performance is fault sharing. So let us say one of the threads is just incrementing some variable, right? And another thread is also incrementing a different variable. So these two variables have nothing to do with each other, right? They are independent variables. But as it turns out, on the physical page, X and Y are on the same physical page. Okay, so now what will happen? So let us say this is running on a worker 1, this is running on worker 2, right? So when worker 1 tries to access X, it will say I need this page, right? So it will go and get it from W2, right? So this page went to W2, W1 made some modifications to X, right? And then W2 says I want to access Y. So the page has to go back to W2, right? It makes its modifications to Y, and then so on, right? So even though they were independent variables, they had nothing to do with each other. We didn't have to use any locks, but just because they were on the same page, we have what is called a ping pong effect, right? The page is ping ponging between two workers. And as you can imagine, this can be terribly slow, right? This just completely kills your performance. Okay, so how can we solve false sharing?
You can pad make sure that those two elements don't appear on the same page by doing some padding.
Instead of sharing pages, we can instead share lines of cache.
Yeah, so instead of sharing pages, so the problem is the page is too large, right? If I had very small pages, then the probability of false sharing reduces, right? So instead of having 4 KB pages, let us say I have only 64 byte something, which is equivalent to a cache line. So then the probability of false sharing reduces, right? So that sounds like a good idea. But the problem is if you reduce the size of the page, then you have lots of pages to track, right? So who has the page becomes a problem, right? So for instance, currently we might have some sort of a central server, let us say, which is the job of this is just keeping track of pages, right? So if I give it a virtual address, it tells me which worker has the page, right? But if I reduce the size of the page, then this mapping will grow very big, right? And the traffic that central server will start receiving will also grow big, right? So the central server itself will become a bottleneck, right? Because it is not able to keep up with the page requests. And we also, by the way, have to worry about fault tolerance of the server itself. What if this goes down, right? So the other problem, and which is actually the most killer problem for DSM, is fault tolerance, right? So I was running for x plus 1, right? Everything is going well, but the W2 which owns this page actually crashed, right? So now I can't access x anymore, right? So remember, pages are distributed, right? Every worker owns a subset of the pages, right? And on top of it, we are trying to create this abstraction of a unified virtual address space, right? So now I was trying to access a page, but the worker that held the page crashed, right? So now the computation is just stuck, right? As soon, even if you lose a single page, there is a problem, right? Because there is no way to get that data anymore. And the similar issue is with straggler. So let us say W2 is really slow. So you are trying to get X from it, but it is taking its sweet time to return this because its network is slow or whatever, right? And the whole computation is just stuck, waiting for X, right? Because you cannot move forward from here until the page fault is serviced. Too bad. So any thoughts? Any questions on this? Any thoughts on fault tolerance? Can we do something about it?
To protect it, we can have copy.
We can keep copies.
Like we could also save the state of the pages at a particular state of time. So like if there any fault occurs, we can
Okay, brilliant. So we came up with two approaches to fault tolerance, and these are actually two regularly used approaches, right? So one is called checkpoint, right? So the idea seems to be that we will store all the pages to disk at some point, right? And when the computations, when things crash, we will bring the page back from the disk, right? Something like that, hopefully. So any problems with checkpointing?
Overhead.
Yeah, so there is checkpointing overhead, right? You have to now start save these checkpoints, right? Then how regularly should I checkpoint? Should I checkpoint every 1 second? Should I checkpoint every 1 minute? Right? So if I checkpoint too often, then I may have too much overhead. But if I don't checkpoint too often, then if there is a fault, I have to go back in time, right? So the other issue is once you have how to make the checkpoint, right? So let us say one page. So remember computation is running at the same time, right? So someone is modifying X, Y, and Z, and maybe you are making checkpoints at the same time, while the computation is running. So then that can get pretty messy, right? You saw a certain value of X, which was supposed to be 2 into Y, but Y didn't see that same value, right? So, so this is called the consistency of checkpoint, right? So let us say X was on one page, Y was on another page, and X was supposed to be always 2 into Y, let us say, right? So Y equals 1, we create a checkpoint at this point for this page. Then we changed Y equals to 2. And then we changed X equals to 4. Right? So X was initially 2. Right? And then we make checkpoint for X equals 4. Right? So now we broke our semantics that X has gone ahead of 2 into Y. Right? That should have never happened. So creating these checkpoints in an asynchronous manner could be pretty risky, right? If we let computation then at the same time while we are creating the checkpoints, we can have all kinds of issues. So how to create a consistent checkpoint? Maybe we can do synchronous checkpoints. So we will say stop the computation. Everyone just stops, creates their checkpoints, right? And then everyone resumes and continues. Right? But that's also expensive, right? Because we stopped the computation for everyone, created the checkpoint. Then another issue is how to roll back to the checkpoint, right? So let us say you created checkpoint, after that you did some network communication and things crash. So now you want to roll back your computation to the checkpoint, so we'll start again from the checkpoint. But what happens to this network communication that you made? How do you roll back what you already told someone?
After checkpoint, if we commit it, then we can roll back, right? Kind of saving the state.
Right. So this is something to worry about, right? How to roll back to the checkpoint. So this is one approach towards fault tolerance, right? And it comes with its own host of problems. Then the other approach that someone mentioned is replication, right? So instead of writing once, I will write it 3 times. So even if 2 crash, I still have a copy of the page, right? So every time I'm modifying X, right? So the same, every page has 3 copies on 3 different machines. So when I'm modifying X to 3, I will change it on all the 3 pages, right? So even if one page crashes, I still have the value of X. How do we like this?
The problem of consistency is still there.
Yeah, so the one problem is inconsistency. So what if I am not able to write to this guy? Can I let the computation move forward?
Is this happening concurrently?
Yeah, so the idea, the proposal is every time I'm modifying a page, I will modify it 3 times, right? So every page is held by 3 different workers, and I will tell the new value of X to all 3 of them, right? So even if one worker crashes, I still have a copy of the page, right? We get the idea of replication, right? At least the proposal of replication. But first problem is local lights became remote writes, right? So something I was just changing the value of x locally, which may be even my cache line. Now I have to change it over the network, right? Every write has to go over the network, right? So this will be extremely slow, right? Every local write became a remote write. Then secondly, how do you manage the consistency? So if I'm unable to talk to this guy, what should I do? Should I pause my computation? If I paused my computation, then maybe I'm not fault tolerant because maybe that worker had died. So now the computation is stuck forever. Or maybe the worker was not responding for some time. I let the computation move forward. So these two guys think x is 5, but this one still thinks x is 3. So now I have this divergent pages, right? And if someone uses this page when accessing x, then we have issues in our correctness.
We can have timestamp
And it's not
Like we need something like we can have a caching
timestamp or
which will later when they choose.
you can add a TTL.
TTL,
Time to
right? So these are some ideas we will see throughout the winter school, right? How to create checkpoints, how to do replication in a way that we can have good consistency, right? While being fault tolerant. But these are some of the issues, right? These are very hard problems, and researchers have been struggling with them for multiple decades, right? So you can see it's pretty hard, but also fun, right? Hopefully. No one agrees with me. Okay, so basically DSM is a brilliant idea, right? Because whatever program I had, I could just run it without any modification, right? So I don't have to think about distributed computation at all, right? Hopefully, if DSM works. But that is the promise of DSM. But it struggles with all of these problems, right? How to do fault tolerance, how to do straggler mitigation, how to deal with fault sharing, how to do bookkeeping of the pages, and so on. Right? So what the community, research community, so this was a hot topic in 80s, right? People were trying all kinds of DSM, right? Let's do DSM. So we just looked at a OS level DSM, but there have been approaches trying to do hardware level DSM, trying to do language runtime level DSM, right? So you do DSM inside JVM. So instead of sharing pages, you are trying to do some DSM over objects, right? Stuff like that. But overall, it doesn't seem to have taken off because of these problems, right? So what the research community have more recently figured out is doing general purpose computation is quite hard, right? So can we give up on, let's just give up on general purpose computation. It's quite hard. So the idea is, can we build some different abstractions for different flavors of computation, right? So hopefully some computation is so common that I can build a specialized system for it, and it just works for that sort of computation, right? So you can see there are systems for, so batch is also a very big umbrella. But there are systems for batch computation, streaming computation, ML model training, right? Graph computations, and within them there are many, many systems, right? So we are not trying to solve a general problem of distributed computation. We are just trying to provide some abstraction which is hopefully useful for a lot of computation, right? But if you try to step out of that computation, step out of that abstraction, try to do something that it doesn't support, then you may see issues, right? So this idea was popularized by Google in their paper called, seminal paper called MapReduce, right? So MapReduce says that we will not try to support general computation, right? That is the big idea here, right? So people are struggling to support general computation, right, and running into all of these issues. So their big idea, really, the big idea is we will not support general computation, right? So we will only support computation containing map and reduce functions. And if your computation fits into map and reduce, then we will take care of everything. We'll take care of fault tolerance, we'll take care of straggler mitigation, we'll take care of auto parallelization, scalability, everything. Right, so let's look at let's first look at what is MapReduce. Then we can see why MapReduce made sense, and then finally see how the system works. So let me first show you the abstraction. By the way, any questions before we move on to MapReduce? Okay, so this is the this is still a pseudocode, but this is the programming interface that MapReduce gives, right? So this is not, you're not trying to write arbitrary C programs, right? Not trying to manage arbitrary pointers, right? You have to structure your computation as map and reduce functions, right? So this is the word count that you wrote in the lab yesterday using MapReduce, right? So the idea is that every file, so this is the file name, this is the contents in the file, right? So this mapper function is just going over the file contents, right, and emitting every word, right, that I saw this word, I saw this word, I saw this word. So it's mapping files to words, right? Then the reduce takes so now the key is the word and values is a list of counts, right? So it is parsing the counts and just adding them up, right? So I got one word, let us say hello, and the list, this will be the different counts of hello seen in different files, right? So the job of reduce is to sum them up, right? So the reduce function is just summing all the counts for the particular word. The map function is mapping a file to words. Clear? So the interesting thing is we are moving away from general purpose computation, but MapReduce can still solve a surprisingly large number of problems, right? So it's a very simple interface, but it can still solve a large number of problems. So let us say we are trying to do grep. That is, we are trying to find words in a bunch of files. So how will you write map and how will you write reduce?
Can you please go back to slide?
Yeah. Actually, let's just do it here. So map should probably take the file, right? Same as word count. So it takes the file and file contents, right? And we also know the word that we want to search. So maybe that is available somewhere, right? So grep, hopefully everyone knows grep, right? Grep is searching for some regular expression or some word in a bunch of files.
You can immediate if word matches.
Right. So if word matches, if word is present in the line, right? So we'll go line by line in the file. If word is present in the line, then I can emit it, right? So this will emit the line that contains the word, right? So there is a if condition above the emit, right? And a for loop. So I'll iterate over the lines in the file. If the word is in the file, I will emit it. Then reduce is simple. Reduce will just append all the lines, right? So and the output will be the distributed grep, basically grep. Let's just get more familiar with MapReduce. Let's look at another example. So let us say I want to get reverse web link graph, right? This is what Google wants to do. So I have a big graph, right? Very big graph. And I want to know for every node which documents point to me, right? And what you are given, so each of these are web pages, right, or documents, right, and the documents are pointing to other documents, right? So I want to know which documents are pointing to me, right, for every node. So one way to write this, or the way to write this map is it will take the source document, right, and it will parse the document, and anytime it finds a link, it will emit it, right, for all links, right? So parse the document, if I see a link, emit it, and then reduce gets all the links for a particular target, right, and just appends them into a list. So you end up with, for each target, what is the list of sources. Does it make sense?
So our doc is like an HTML page.
Yeah.
Should we emit the target as well, or
Huh?
should we emit the target as well?
Yeah, we have to emit the, yeah, so when I meant link, this is the target source tuple. Right? Okay, so MapReduce is useful across a number of use cases, and the promise of Google is that we will make this run in a highly scalable manner, and will take care of fault tolerance, straggler mitigation, and whatnot. Right? Okay, so we should let's also.
I have a doubt in MapReduce. Suppose we are not searching something, we are modifying it. What
You can't. I mean, as long as you can specify as map and reduce, you can do it. If your computation doesn't fit in map and reduce, you can't use MapReduce. Right? So let's again understand this a little bit more, what it means and how it works. So let us say these were my input files, and I'm back at word count, right? So I'm trying to count the frequency of every word, right? So the job of the mapper is to go over every file and emit anytime it sees a word, right? So maybe it saw 2 A's and 1 B's. So it will call a API called emit intermediate for the word count, right? And here as well, it saw 1A and 1B, right? So now all the A's will be collected for reducing, right? Right. So the system will collect all the A's, right, and give this to the reduce function, right. So the map function is doing this file name, file to words, right, and the reduce function is doing this word and iterable to an aggregation, right. So this part is written by the programmer, right, that how to turn an input, how to map the input, and this part is also written by the programmer, right. And these are the only two parts that they need to write, right. What is the map function, what is the reduce function. And the system will automatically take care of the rest, right. So in this case, all the A's went to a particular worker, right, and that did the summation of A to 3. All the B's will probably go to another worker, right, and then again the reducer function written by the programmer is invoked, and B is written as 2, right. So this is the paradigm of MapReduce. Any questions how this works and what the programmer is doing? Okay, so let's before we look at the actual system, how they are doing straggler mitigation and whatnot, we can think about why MapReduce. And this sounds pretty random. Why not anything else, right? So we can look at how it might be getting executed. So let us say we have M map tasks, right? So these map tasks can be M files that I'm turning into words, right? So I have M map tasks. Each map task takes M time, small m time. Then let us say I have R reduce tasks, right? Now reduce tasks are for every word, right? I have to do an aggregation, right? So I have R reduce tasks, and every reduce task takes R time. So what is the serial runtime of this? Plus RR, right? Right. So I have M map tasks, each taking M time, then R reduce tasks, each taking R time. So, but now to run it in parallel, each map task will write some output for every reduce task, right? Right. So every map task will write R outputs, right? And then the first reduce task will take the first output from all the map tasks, and so on. The second reduce task will take the second output from all the map tasks, right? So this is so maybe the first reduce task was reducing A, the second reduce task was reducing B, right? So every map task generated output for all the reduce tasks, right? And a particular reduce task will get its input from all the map tasks. So let us further assume that the size of this is some constant C, right? So again we are back in the analytical land, by the way, right? We are making very happy assumptions, right? So now what is the parallel time of this? So the first is I have to run this computation, right? So maybe I will split computation by giving M over P tasks to every worker, right? So first is this M over P multiplied by M. Then I will also give this R task or R over P tasks to each worker, right? So this is my computation time. But the additional overhead is communication, right? So in serial, when you were executing this serially, everything was in local memory, right? There was no communication overhead. But now this reducer has to get its inputs from all the mappers, right? So a particular worker has to get R by P, has to get inputs for R by P reducers. And for each reducer, I have to get inputs from M tasks, and I already have input for M by P task, right? Because M by P task was on my local worker. So let me color code this. So all this is being done by worker 1, and this is also done by worker 1. This was being done by worker 2, and this is being done by worker 2. Right? So worker 1 already had data from M over P tasks. Right? So I don't have to get inputs from those. And then I multiply C with it, right? So my TP becomes 1 by P MM plus RR plus MRC, right? So into P minus 1 over P.
How did we get R by P?
So R by P is the number of reducers running on a worker. So this is the communication cost, right? So I have to get inputs for R by P reducers, right? A worker has to run R by P reducers, right? So it has to get inputs for R by P reducers, right? And then for every reducer has to get get its input from M minus M by P mappers, and the size of every input is C. Okay, so as you can see, okay, so let's keep doing this. So P is 1 over P. Right, so my speed up, let's directly talk about efficiency. So my efficiency is what? TS over PTP, right? So MM plus RR. Right, this is my efficiency. So this is a pretty good efficiency, right? So if P is large, right, then this tends to 1, right? If M and R are large, then I end up with a nearly constant efficiency, right? So this is a class of problems that are called embarrassingly parallel programs, right? Because they have just so much parallelism that could be used for making them execute efficiently, right? So let's look at an execution timeline of this. So again, let us say this was running on 4 different processors. So initially, everyone can work on the map tasks, right? Right? Then when the map task ends, they have to exchange information, right? So maybe initially these two exchange information and these two exchange information. Then in the next round, this exchange informations with this one. And let me use a different color. In the second round, this exchange information with this, and this exchanges with this. In the third round, this exchanges information with this, and these two exchange information. Right. So this is the this is the shuffle phase, what they call the shuffle phase, that the reduce task has to get the input from all the map tasks. Right. So after everyone has the inputs that they needed, then they can just run the reduce task. Right. So we are able to use most of the time for computation. Right. The only overhead that we have is during this exchange. Right. This is the only communication overhead. Right. The rest of the time we are able to spend on computation, and we are able to, as long as M and R are much greater than P, no worker has to sit idle. Right. Every worker will have something to do as long as M and R are greater than P. Right. Okay. Any questions? So by the way, we have still not started talking about the actual system, right? How it does fault tolerance and whatnot. We are just looking at the abstraction and trying to see why this abstraction. Are we lost, or are we still following? You have to implement this in lab, by the way. So I hope you are still with me.
So what improvement does this provide over general distribution?
So this will take care of fault tolerance, straggler mitigation, everything, as we will see shortly. Right. So all they are saying is, as long as you write your program in MapReduce, we will take care of everything for you. But you have to write your program as a map function and a reduce function.
But in like general one, if we like duplicate threads for fault tolerance, would it be better than this? Like ultimately, total threads.
Yeah, so that is a system question. So let us, so currently I'm just laying out the constraint of MapReduce, right? You have to use this programming model. So let us look at how they do fault tolerance, straggler mitigation, and so on, and then we can get back to that question, right? Why is it better than DSM?